Okay, hello everyone. Good night, good morning, Miss Kim and Mr. Vincent. How are you today?
I'm fine. How are you?
Okay, fine, thank you. Okay, thank you for joining us to this today's session with Volcano International Volcano Academy Volume 2, and this discussion forum providing by Ichian Geopark and Geostoria, which has goal to socialize the result of the several volcanological research. And this forum has a purpose to bring together and to discuss between society and researcher to make the result of the research make a better impact to our planet, especially for local people. Okay, I will tell you about the random of the today's session. The first one, we have opening remark from management of Ichian Geopark, and then the material from Miss Kim, and the next material from Mr. Vincent, and the last one is Q&A session. So that is okay, Miss Kim and Mr. Vincent.
Yes.
Sorry, maybe. Okay. Let's just start. Maybe I'm sorry for a little bit late for everyone in Indonesia. But first of all, I will give like some disclaimer to our friend from Indonesia that maybe cannot speak English. Is that okay, Mr. Vincent and Miss Kim?
Yes, of course.
Oke, teman-teman, selamat malam. Terima kasih waktunya sudah menyempatkan pada malam hari ini bergabung di International Volcano Academy. Kita malam ini akan membahas tingkat keasaman dari Kawah Ijen yang akan disampaikan oleh Miss Kim dan Mr. Vincent dari McGill University of Canada. Untuk teman-teman nanti sesi pertanyaan akan ada di akhir setelah penjelasan dari narasumber. Nanti bisa yang tidak berkenan open mic bisa via chat, tapi alangkah lebih baiknya jika disampaikan secara langsung menggunakan fitur raise hand. Tidak masalah jikalau tidak berbahasa Inggris, kurang bisa berbahasa Inggris, nanti akan kita bantu untuk translate agar komunikasi kita juga bisa berjalan lancar. Miss Kim dan Mr. Vincent mengharapkan adanya partisipasi yang cukup kuat dari masyarakat lokal. Jadi nanti di akhir acara beliau ingin banyak berdiskusi daripada menyampaikan materi. Mungkin seperti itu. Oke, thank you. Let we start the first one. We have opening remark from management of Geopark to Mr. Abdillah. Time is yours.
Okay, thank you, Fikli. Good night from Indonesia. Good morning, Prof. Kim and Dr. Vincent. I hope you are always fine. I think you have a good memory studying in Ichian several years ago, and I'm sure you already miss it. I'm Abdillah from Ichian Geopark Management. On this excellent opportunity, I would like to say thank you and welcome to the International Volcano Academy Forum. As an UNESCO aspiring global geopark, Ichian Geopark must appear on the international scene as one of the learning centers in the world. We have 10 cultural sites, 6 biological sites, and of course, 21 geological sites. Several of them is related with volcanism. The science of volcanology is important because it is closely related to society and the main theme of this geopark. We have a subduction system that produces 30 million years old volcanoes. We also have an active volcano that's just erupted this year. We have calderas, cinder cones, submarine volcanoes, crater lakes, fumaroles, solfatara, hot spring, and so on. We have Kawah Ijen, the most aged crater lake on our planet. The crater is our main geological theme, but I am sure that behind its majestic phenomena, Kawah Ijen have a lot of secret that we all doesn't know yet. So this discussion will greatly add to our explanation regarding this. However, on the other hand, interest related to volcanology is still need to be increased, especially for young people. We hope that in the future there will be many volcanologists who take care of the volcanoes in the Ichian Geopark. Therefore, we initiated a discussion forum with international volcanic research to gain wider experience and knowledge about volcanology. We hope that through this forum, we can establish cooperation and collaboration in the fields of research, education, and especially volcanic disaster mitigation in the future. We hope that the Ichian Geopark will become a center volcanic studies, not only Indonesia, but in the world. Thank you very much. Welcome to today's discussion. Thank you.
Okay, thank you, Mr. Abdullah, for the great opening remarks. Mr. Abdullah from management of Ichian Geopark. Thank you. And the next one, we have material from Professor Kim with the material, the hyperacidic crater lake on Earth. Before her speaking, I will read several background from her. Prof. Kim Berlo is currently working as a researcher in the Department of Earth and Planetary Science, McGill University, Canada. Her research interests include volcanic eruption. She studied volcanic rock and gases through observation in natural samples and experiment to find out more about the nature and timescale of magma degassing. She is served an editorial member and reviewer of several international reported journal. Ms. Kimberlo is the member of many international affiliations. She has successfully completed his administrative responsibility. She has authored of many research article or book related to the volcanic eruption. So, for Ms. Kimberlo, the time is yours.
Well, thank you for the invitation to this forum today. I'm really glad to be able to see so many people here today. Vincent and I have been working together on Kawah Ijen for quite some time, along with many other people. And we decided that we were going to set up this presentation together. So in fact, we've set up one presentation and we'll be taking turns in leading this presentation. So the first part will be given by Vincent van Hinsberg. Vincent?
Okay, let me share my screen. So I hope you can see my screen. You see the presentation? Okay.
Yes, of course.
Okay. Well, I think Pa Abdillah introduced us very nicely and introduced the Ichian caldera complex and Kawa Ichian very nicely as well. And as Kim said, we are very grateful for all the help that we've had while we conducted fieldwork at Ichian. Help from, of course, the volcano observers, help from people in Paltuding, the people in the homestays in Plawan and St. Paul. Without all of you, we would definitely not have been able to conduct all this field work and get these really exciting research results. And so we're very happy that we get this opportunity to tell you something of the research findings that have come out of that research, and that allow us to slowly get a better understanding of the Ichian caldera complex, Kawa Ichian within it, and how such a volcano actually works. And let's start. So we are located in Montreal, in Canada, and yesterday we had our very first snow of the season, unfortunately. So we're any opportunity that we get to go to warmer and nicer places, we definitely will take. So let's just let's see. Let's hope this works. So let's go from here to Kawa Ichian. So Kawa Ichian is all the way on the other side of the world in East Java, and so it's a stunningly beautiful system. But also scientifically incredibly interesting for a lot of its features. And here we see this Google Earth view of Kawa Ichian with the beautiful lake on the flank of Merapi volcano. And as Pa Abdillah said, of course, everybody knows Kawa Ichian and the Ichian caldera complex because of its crater lake. And this is indeed very interesting. It's the largest acidic crater lake in the world. But the Ichian system is bigger, and there are a lot of other very interesting things within the Ichian caldera complex. Okay, so this is just a map view. So here you can see the structure. Bali is over here, Banyuwangi is here, and so this is where Kawa Ichian is located. And so we have Merapi volcano here, and you can see that you have this large highland here, the Ichian highland. And so Kawa Ichian is only a small part of that much bigger structure. And we also have Raung volcano right next to it, which is of course also an active volcano. And so you can see that that although Kawa Ichian is very interesting, it's part of a bigger system. And also, if we want to understand that system, we need to understand its relationships to the other parts of this volcanic system. And Kim will talk more about this. So let me just start with a few nice pictures. And so this clearly is what everybody thinks of when they think of the Ichian system, and that is the crater lake of Kawa Ichian. And so very interesting. Dangerous as well, but a beautiful setting. The other part people think of is the fumaroles, and so here you see the fumarole mount and all the sulfurous gases that come out of that system. And it's not a very large fumarole mount, but the reason people know this well is because of the sulfur mining that takes place here. So already going back to the 1790s. People have been mining sulfur from this sulfatara, and so they condense the gases and they collect the sulfur here. But as I said, there is a lot more to the system. So let's have a look at some other parts. So this is the upstream Banyupayit River. This is an acidic river that comes out of the crater lake. It has a beautiful valley, lots of waterfalls. Beautiful colors because of the reactions of the water with the rocks. This is even further upstream. You have these lava flows that are carved out. And then if you go all the way to the other side, so we go to the caldera rim, we find this waterfall in the Manyuputi River. Really nice setting here. And here on the other side, you can see this very flat plain, and that's actually a fault plain. That is here very nicely exposed. And it's along that fault that the river found a way to leave the caldera. And this is just an overview of the caldera, the Ichian caldera. We have Raung volcano here and a number of other volcanoes in the system. Because it's important to remember that Cave Ichian is not the only volcano within the Ichian caldera. There are actually quite a few. And again, Kim will talk more about this. And here we see Raung very nicely in an evening view. And then the other thing that that attracts all the tourists to Cave Ichian is the blue flames. And so this is where gases from the fumaroles, as well as the sulfur itself, they're essentially on fire. And in the reactions that happen, light is emitted, and that light has a blue hue to it. So at night you can see these beautiful blue flames. It's beautiful, but and so yeah, Cave Ichian is beautiful, but it's also important to remember that Cave Ichian is also an active volcano, and it's an active volcano in a setting where people live. So on the Ichian highland, you have quite a few coffee plantations, and with that several villages. And you can see, sorry, the proximity to Cave Ichian. So here you see the plume coming out of Cave Ichian, and you can see how close that actually is to these coffee plantations. And also, just on the outside flanks of the volcano, we find the harbor city of Banyuwangi. And this is the main transportation hub between Bali and Java. So, so Cave Ichian definitely has a volcanic risk associated with it because of that. And that risk is very clear if we go back to the last major eruption of Cave Ichian, which happened in 1817. And so in that eruption, the crater lake was thrown out, and there was a big eruption column, and there's several explosions and other things. And so what happened in that eruption was that lahar traveled from the volcano, and this was because of rain as well as the water that was in the crater lake. They traveled along the river valleys all the way to the north, onto the outer flanks, to the Asam Bagus plain. And on the other way, they also traveled down the volcano to Banyuwangi. And so this was quite a large event. And so the information on it is not very detailed, but we know that there was about a foot of ash deposited in Banyuwangi. And a lot of the crater lake was at that time also concentrated like it is now. And so that deposited a toxic mud on farmland. And so for years, it was actually very difficult to farm in the area. Now, the only good thing about it was that, as far as we know, there were no casualties associated with this event. But in part, that was because there were not many people living here at that time. And now, of course, it's quite different. So the city of Banyuwangi is a very large city, and also towards the Asam Bagus plain, there are quite a lot of villages. So we have to really think also about the volcanic hazards of the Cave Ichian system. If we then, so what do we know about what the volcano was like in 1817? We have some information from a visit in 1805, so just before the eruption. And so we know that Cave Ichian at that time did have a lake, similar to now, but the crater did look quite different. So the upper image here shows what the crater looked like in 1817. The lake was small, the fumaroles were on this side of the lake, and it was not as deep as it is now. And so this, for comparison, is what the crater looks like now. The lake is a lot bigger, and the fumaroles have shifted as well. And in fact, if you look at this image here, which is a photograph of the crater, we think that this level up here represents the lake level at 1817. And these are all lake sediments that would have been underneath the water at that time. So the crater has deepened quite a lot. And if you look at the crater shape, we can recognize that you have a number of these nested craters that suggest that this has happened multiple times. So there have been several eruptions through this crater, and we have some evidence that they involved fluids as well. Okay, so Cave Ichian clearly has a volcanic hazard associated with it. So that means that you really need to understand this system from that perspective as well. Okay, so that brings the obvious question. Okay, so what will happen in the future? And I'm sure many people wonder, okay, so is Cava Ichian going to erupt again? And when will that be? And what will that eruption look like? Now, with the current understanding that we have of the Ichian caldera and the Cava Ichian system, we can actually not predict what the future will bring. So we still need to do quite a bit of research to understand the system better so that we can actually do that. But so how do we address that question then? There are basically two ways. Since about 2010, there's been a very detailed and very comprehensive monitoring system at Cava Ichian. And so this monitoring is done by the Ichian Observatory in Ichian, as well as CVGHM. And they now have access to seismometers in the crater, gas monitoring, deformation monitoring, sound observations, video, etc. So Cava Ichian right now is very well monitored. And the idea behind that monitoring is that whenever there's a change in the volcanic system, it will be detected straight away. And so with that, they're now able to really see any change that's happening in the system and provide any warning should anything be happening. So that's very good. And then the second component to that is that we need to understand the volcanic system better. So for that, we actually go to the past and we see what the volcano has done in the past. And we can use that to predict what the system is going to do in the future. And it is this component of this research that we have contributed to. So I'm not going to talk about the current monitoring. If you're interested in that, I highly recommend that you get in touch with the Ichian Observatory. They are the experts in this. So we will talk about this question of how can we understand the volcanic system and how we can use that to predict what it may do in the future, and how you would best monitor this. And so this all, what we've decided to do is this presentation is all about this image here, which is a schematic cross-section through the volcanic system. So if you would cut right through Cava Ichian to great depth, then this is what we think you will find. And so this really helps. So this is a conceptual model. So this is a model for the volcano, simplified, but has all the important components in it. And that is based on, it's not just our research, but research by people who have been conducting that for the last at least 100 years. And when you synthesize all of that together, then this is roughly the model that you come up with. And that is very useful, because such a model we can then use to take all our observations and link them to what is happening, for example, at depth in the subsurface or happening somewhere else. Okay, so and so how do we actually figure this out? We look at everything that you can observe on the surface of the volcano. So we looked at rock samples that were erupted in past eruptions, but also lake sediments and other deposits. And they tell us something about what Ichian was like in the past and what happened in past eruptions. We can also measure the volcanic gases that are coming out in the fumaroles. And they tell us something about what's happening to the volcano right now. We can look at the fluids. We have, of course, our crater lake, but we also have some fluids that are coming out and forming a river, the Banyupait River. So we can look at those as well. And then we have some mineral precipitates that form from those fluids, in particular the mineral gypsum, and they give us a time series of what happened in the recent past. So we can combine all of those things together, and this is then the model that we come up with. So we're going to discuss the different parts of this model. We're going to start with the magmatic components and move to the gases, go to the what the fluids can tell us, and we're going to end up with what gypsum can tell us and a little bit on volcano monitoring. Okay, so I'm going to pass it on to Professor Burlow now.
All right. All right, so I'm going to take a step back and look at the Ichian caldera complex as a larger picture. So next slide, please. Right, so Ichian lies above a subduction zone where the Indo-Australian plate subducts underneath the Eurasian plate, and this subduction causes the earthquakes and the volcanism that we see on Java. Next slide, please. So Kawah Ijen is the only active volcano in a larger group of volcanoes, which includes an ancient edifice which was there prior to the caldera forming eruption. Of that caldera forming eruption, the crater rim in the north of the caldera rim in the north of the volcano is still visible. This is I apologize if I pronounce the names incorrectly. The Kendang Wall. And it is bridged by the Banyupite River, which is called Banyuputi at that stage. So this is what's left of that Ignimbrite eruption. There's very little still known about this eruption. So we only have this northern semicircle. The southern half of the caldera appears to be buried underneath some post-caldera volcanism. So these are large volcanoes, Jumpit, Arante, and Merapi volcano, as well as Kawah Ijen. And the caldera floor appears to be tilted towards the north. Then there is Raung volcano on the left side of this image, which is also an active volcano, and its relation to Kawah Ijen caldera is still a bit unclear. It is a very large volcano. It has a similar sort of footprints to the Ichian caldera complex. In composition is very similar to Ichian caldera complex, but its exact relation to the caldera is still uncertain. Next slide, please. All right, so here we see a satellite image, and we can see that Kendang Ridge on the left side, upper left side of the image. So that was the remnant of an edifice that might have been there before the collapse. And on the south side, we see those large volcanoes, so Merapi, Ranti, and Jumpit, that appear to lie on the buried southern edge of that caldera. Next slide, please. Now, in the interior of the caldera, there are several smaller vents, and these are younger as well. So we see Anjar, Genteng, Telagaweru, Pencil. All of these are younger. They're small scoria cones that have produced quite large lava flows, and they all flowing towards the northern edge of the caldera. And we can still, and these are actually, this is relatively young volcanism. We can still clearly on this image see the lava flows in the caldera floor. And also in the field, these are quite prominently visible. Next slide, please. So all of these intracaldera volcanoes appear to lie along some sort of structural trend that extends from Kawah Ijen towards, in the direction of Raung volcano. It doesn't go all the way to Raung. And we can see that the Banyupite River also initially follows that same trends, which lends further suggestion that this is an important underlying structural feature in the caldera. Whether it's a fault or a dike, we don't really know at the moment. Okay, next slide, please. So here we see the same linear feature in map view with the ring volcanoes, the ones that lie on the caldera. And then we have the ones that lie inside of the caldera as well. Next slide, please. Here we have an overview picture that was taken in 2014. And we can see in the upper image, we can see we're looking north towards this Kendang Ridge in the distance, and the gap through which the river leaves the caldera. On the southern image, we can see the Genteng cones, cinder cones, as well as the lava flow in the foreground. And in the background, in the far background, we see Raung volcano, Sukkot volcano, and just visible, we can see Anjar as well. On the left, we see Jumpit in the distance. Next slide, please. All right, so to find out more about the geological history of the Ichian caldera complex, a geological map was made in the 80s. And making such a geological map is a huge undertaking, and it's essentially the basis for all geological research. And so all of what we're doing is based upon these sort of maps. So if you're unfamiliar with a geological map, this is a map of the caldera. We can see the northern caldera wall in green, the canyoning wall. The linear feature that I mentioned before is the dashed line. And all the colors on a map like this are different geological units. So we can see lava flows in pink extending from Kawa Ichian. And we can see the other lava flows from Anjar and Genting, all flowing from that linear feature toward the north of the caldera. Next slide, please. Okay, so what we can also learn, so these sort of maps are made by looking at the rocks and comparing them from one place to another. We can also look at these rocks in a bit more detail. And the rocks give us information about the state of the magma prior to eruption. So on the right, we see a rock sample, the one with the pen next to it. And we can see this bright white line in it. So this is in fact a bomb that was thrown out in 1817. And this white line indicates that there was a different composition of magma that mingled in at the time of the eruption. We can also see some smaller white dots, which are pleasure clay crystals. And they give us information about what might be going on in the magma chamber. So on the left side image, we can see a thin section, a slice of the rock, a very thin slice of the rock under a microscope, and we can see the individual crystals in white. So these are those pleasure glaze crystals that I mentioned before. We can also see that the sort of brown and gray colors, the matrix, and we can see that there's different colors in that as well, which is the same reason that I mentioned that white line. So there is some magma mingling happening at the time of this eruption in 1817. And so the texture and the composition of the minerals hold information about the magma chamber. The chemical composition of the entire rock, so if we crush it up and we analyze the whole rock, also holds information. Next slide, please. So let's look at what that can tell us. So here we have a study by Heather Handley, where they've analyzed these rocks from Kawa Ichian from all over the caldera. And what we find is that there's in fact two trends. There's the blue trend, which is comprised of rocks from these intra-caldera volcanoes. And then there's the green trends, which is the ring volcanoes. So these are the older, bigger volcanoes on the southern caldera edge. And they form different chemical trends, which are consistent with different minerals crystallizing at depth. And from the type of minerals that are crystallizing in these rocks to form these trends, we can tell that the ring volcanoes tap a deeper magma than the intravolcano volcanoes. So there is some shallower magma chamber at the time of eruption of the intracaldera volcanoes than there was at the time of eruption of the ring volcanoes. Interestingly, Kawa Ichian plots along both the shallower trends, so shallow volcanoes, and the deeper trends. And when we go back to the map in the next slide, please, we can see that Kawa Ichian lies along the intersection between, so it lies just off the caldera edge, and it also plots on that line that extends from Kawa Ichian towards Gunung Rang. Next slide, please. Okay, so let's look at the last eruption from Kawa Ichian. So as Vincent mentioned, so this was in 1817. And so we're particularly interested in Kawa Ichian because it's the most recent active volcano and has the most recent volcanics. And so we're also interested to see, should an eruption happen, what that might look like. And we can look at the rock record again to help us and to give us information about that. And so when we do that, we can see that we know from the records that there was a lake prior to 1817 as well, and that lake was also previously erupted, and so that lake has been emptied before that eruption as well. So this is a recurring feature, and we know that because we can see these phreatic and phreatic magmatic deposits, which have abundant altered materials, so all the colors, the white, the pink, and the orange, within the rock records. So this theme of having a lake at Kawa Ichian and having it erupt and empty and then refilling is a recurring thing at Kawa Ichian. And this lake in the past was acidic as well, as we can tell from the alteration. Next slide, please. And can you get me the other ones as well, please? Just click again, thank you. All right, so here we see a stratigraphic column. So this is just a section through eruptive deposits, whereby the older deposits, so the things that happened first during the eruption, are at the bottom. So we can see that initially there was some phreatic activity. Again, we see those really white altered colors in the deposits. This was followed as the lake dried out and we no longer see the altered material by some scoria deposits. They're very rhythmically layered. They look like they might be Strombolian deposits, which is consistent with the records that are available, sparse records that are available from that time. And then the eruption ended with some Volcanian eruptions, with thrown out large bombs. The system appears to have been choking, and it ended, according to the records, with a very loud bang. Next slide, please. Okay, so that concludes my section on the caldera. I'm now going to talk a little bit about the volcanic gases. Okay, so if we return to our conceptual model of Kawa Ichian, we can identify at different locations where gases are emitted. So obviously at the fumaroles, but isn't the only place where we can see volcanic gases. There are gases being released underneath the lake. There are gases that are released diffusely throughout the soil in the edifice, the surrounding area. And we also see gases that are dissolved essentially, not just within the lake, but also within the hydrothermal system around the volcano. And that hydrothermal system surfaces on the flanks of the volcano in the Banyapite River Valley. Okay, and in fact, that fluid forms mostly the river water. Next slide, please. Okay, so here we have those famous, beautiful fumaroles again. And they're often shrouded in these thick white clouds, which is in fact mostly water vapor. When you see a yellow tinge to the clouds, it's caused by sulfur. But a lot of the sulfur is actually captured during the mining process, where they condense the gases to get the sulfur out. And next slide, please. And here we see those pipes where the sulfur is being condensed. Next slide, please. Here we have another image. This is in fact an experiment where we stuck in a smaller pipe, a clean smaller pipe, where we wanted to see which minerals condense from the gases as they cool and mix with air. So we took the sample back with us to McGill and analyzed the minerals that were in there. So it's not just sulfur that's coming out of these pipes, it's also a lot of other minerals and elements. Next slide, please. And as I mentioned before, there's also gas going into the lake that was made very clear in this echogram by Corentin Caldron. And it sort of pictures the bubbles as they are coming up through the bottom of the lake. We can see them at the surface as well. So I've heard reports of bubbling happening. I've not seen them myself, but we can see this yellow froth on the surface of the lake, some of which is in fact tiny spheres that are mostly hollow and coated in sulfur. They have some very exotic minerals in there too, but they're mostly hollow. And these are in fact bubbles that come up from the bottom of the lake. Next slide, please. Now, diffuse degassing happens. We can't picture it, but I did want to illustrate this picture here. This is one of the spring areas that feeds the Banyupai River. And when you go here, you can definitely smell that there's gases being released from these fluids as well as they come up from depth. And these gases tend to pool in lower areas. This cave in particular is a place that you wouldn't want to go into because there will be gases pooling there, and it can be quite dangerous because there won't be a lot of oxygen there. So there are gases, and even though you don't see them, stay out of these places. They're cool to explore, but not a good idea. Next slide, please. All right, so if we go back to our conceptual model, we now see that we can, you've seen that we can sample the fumarole gases, we can sample the lake, we could sample the diffuse gases, we haven't done that yet, and we can sample the river water. So let's, sampling of the fumaroles is a challenge. It's equipment doesn't last long in this kind of environment. People last a little longer, but it's not something that you want to do on a routine measure. You can't leave your equipment there to get this sort of time series. But let's look at what has been done in the past, because it has been done by several groups, in fact. And next slide, please. So the fumaroles have been present in the same location for more than 220 years. And so they were actually present in the same location prior to the 1817 eruption, or they were reestablished on the same location following that eruption. And their composition has been analyzed on a number of occasions in recent times. There's no historic records of the fumarole gases that we can compare our measurements to. And this is very unfortunate. When we compare them to, so this is now data from both from us and from the Volcanological Survey, and when we compare that data to the wider area, to the Sunda arc, so on Java, then and further, then we can see that the compositions are fairly normal to what we would expect to find, but the composition of Ichian is a bit richer in CO2. The sulfur flux at Kawa Ichian is 200 tons a day, which is a lot for such a relatively small volcano. Next slide, please. Okay, so that's the CO2 and the sulfur, and a lot of work is being done, that's being monitored very carefully at the moment. But you can also look at all these other elements. I mentioned before that we did this experiment on the sulfur dome with the tube sticking out to look at other elements that are coming out of the gases. And so this is part of that study. So all of these elements, mostly CO2, water, sulfur, but also things like metals, things like arsenic, copper, and antimony are being released by these volcanic gases. And these gases originate from the magma at depth. So they were originally dissolved within the magma, and as the magma cools and rises, it releases them to the volcanic gas phase. And so we can compare these concentrations of these metals and their ratios to what was in the magma at depth. So now we're going to compare surface emissions, current day surface emissions, to older eruptive deposits. Okay, so there's a bit of a time gap there, but we can't access the magma system at this stage. So we're just going to compare modern day gases to rocks, essentially, that were thrown out in previous eruptions. Next slide, please. Okay, so to do that, we can look at melt inclusions. So these are parcels of melt that are trapped as the crystals grow in the magma. And they present the way in which we can look at what might be dissolved in the magma at depth before an eruption. So again, this is an eruption that happened historically. It's not current magma. And when we do that, we can see, and we compare it to the modern day fumarole gases, the comparison is actually pretty good for a lot of the elements. So the compositions match the ratios. There's a couple of elements that don't match, namely things like antimony, thallium, and arsenic. And so our interpretation is that the elements that match, they come from a deeper degassing magma. So this deeper degassing magma is supplying CO2, sulfur, and things like copper and lead, moly, and zinc to our gases. Then the other elements that don't match, they actually match a younger rhyolitic, more felsic magma. So it's a different composition magma. And we see them in the gases. So they are currently degassing as well. So that suggests that there's currently two magmas that are contributing to that gas phase. So a shallower, more felsic magma and a deeper mafic magma. Now this trace element signature, the metal signature of that deep degassing magma, matches a process, the process of the breakdown of the sulfide liquid at depth. So this is happening as a result of degassing. Next slide, please. Okay, so here we have that as a cartoon. So we have a mafic magma at depth. There's some sulfide liquids, sulfide saturated. The sulfide liquid breaks down as soon as it starts to degas and rises. The gases then go into this more felsic magma that's sitting shallower, has to pass through a hydrothermal system, and ultimately we can see that signature still at the fumaroles. Next slide, please. And this is where I hand over to Vincent again. Vincent, your mic's off.
Yes, sorry, I saw that I'm still muted. Okay, thank you. So, so now I'm going to switch to the crater lake and the Banyupaid part of the system. And so Kava Ichian is a so-called wet volcano. And what that means is that this is a volcano where on the surface and shallow depth, we have a lot of fluids. And so fluids are very important then to understand this volcanic system and everything that's happening to it. Now, having so much fluid has both some benefits and some downsides. A problem of this is that any signature from depth, so for example, some earthquakes or some other seismicity, in order for it to be detected on the surface, it needs to pass through this filter over the hydrothermal system, the lake, and so on. So that actually makes it harder to interpret at the surface because there's this filter that changes the signals. So things at Kava Ichian don't look exactly as you would at a dry volcano, such as Gunung Merapi, for example. But at the same time, having all these fluids here also provides some opportunities, because these fluids, they come from depth, they interact with emissions from the magma, as Kim showed. So potentially we can also measure these fluids, measure the crater lake or measure the acid river, and that can tell us something about how the volcanic system works and any changes therein. So we have some opportunities there as well. And so both of these things are being studied a lot. In fact, there are not very many wet volcanoes in the world. They're a small proportion, but they are extremely interesting. And they are also some of the most dangerous volcanoes, because having so much water present, if there is an eruption, then you create a lot of steam. So you create a lot of gas that will then make such an eruption quite explosive. Plus, of course, you can form lahar, where we have muds traveling at high speed down valleys and things. So understanding these fluids is quite important. And so if you think about Kava Ichian, then of course we always think about its crater lake. This is a huge volume of water. So there's about 28 million cubic meters of water. So this is a huge lake. And as has been said several times, this is by far the biggest naturally occurring acidic lake in the world, the biggest volcanic crater lake. And so we have this crater lake here. And most of the sides of the crater lake are very steep and rise up very high, about 200 meters between the lake level and the rim. Except here, this part here, there is a breach. And so here, the lake level is actually very close to the crater rim. So this is just a photograph of that area here. And so in the past, especially after the rainy season, when the lake level went up, the water would occasionally go over this rim and flow down along this river valley, which is the Banyupait River Valley. Around 1900, a dam was built. So you can see that here, a dam was built on this bridge to control that outflow. And so what they did is they would hold back the water, and then once in a while they would flush all this excess water that accumulated down the dam and then out to the sea. And but you can see now, so this is a picture from 2008, I believe. You can see that the level of the lake has gone down a lot. And so where it used to be here, we can see this this line here. There's some gypsum on that line. The water level is now a lot lower. And so this dam hasn't really functioned since about the 1980s. What is very interesting is that whenever they would open the dam and release fluids and thereby lower the level of the lake, they would often have gas coming out, and you had some small gas explosions and things. And so that tells us that all this water is acting as a seal on the gas that is coming out from below. And so gases are present at the bottom of the lake. And then when there are large fluctuations in the lake level, these can come out. And then the second major part of water of this system is the Banyupait River. And so this is a river that flows throughout the caldera. It originates here from the crater lake. And then it flows all the way. It has similarly acidic composition. It flows through the caldera all the way to Blawan, where it then mixes with some neutral waters, reacts, and it gets a white color. And so that is why it is called Banyu Putih from then on. And as Kim showed, it then flows through the caldera rim in this beautiful waterfall, and finally out all the way to the Asam Bagus plain and then into the sea. And if you look at satellite images, so the fluids that come out still have a lot of elements in them. So if you look at a satellite image from that area, you can see a plume of white material in the sea. So this is really the Banyu Putih waters reacting with seawater, and you get a lot of mineral precipitates forming. Okay, so if you then think about this Banyupait River, where does it actually come from? And there are multiple sources for the river. So in part, it's coming from this area here, so very close to the crater lake. And here we have fluids that are seeping through the rocks, and they are emerging in a set of springs here. And so I have some pictures of those springs here. And here, right at the top, you may just be able to make out the dam still. So waters are not coming out just below the dam anymore. This is now about 100 meters lower elevation. And then we get these springs. And so we have some porous scoria deposits here. And there's fluids coming out, flowing out. And they deposit a lot of minerals. So these fluids are very concentrated. And you get, in this case, so the white mineral is gypsum. And the yellow mineral here is a mineral called alum. Okay, so these are fairly small springs, but they're very close to the lake. And these are really lake waters that are coming out. A little bit further downstream, we have a second set of springs. And this is a picture of what they look like. They're quite similar. So again, there is a porous scoria layer here, and these fluids are coming out. And we see gypsum depositing and this yellow alum again. And then the river disappears. So the riverbed is actually dry. And then when we get to this point in the river, this is where we actually find the springs that form the Banyupait River. And so these are very high outflow springs. And I think Kim showed this picture already. So we have a lava flow, and then underneath that lava flow and along fractures, we have a very strong outflow of fluids. We get some gypsum precipitation, but not a lot. And then we have the yellow alum again. And so really these springs here are the source of the Banyupayat River. These ones up here are quite interesting, but they do not contribute a lot of fluids to this. And then when we analyze the compositions of all these springs, the composition of the ones up here are almost the same as the Crater Lake water. So we can say for sure, this is Crater Lake outflow. But these fluids here, and also the Banyupayat, they're a little bit different. And we can show that these are not Crater Lake fluids. And we think that this is outflow from the hydrothermal system directly. So you can see that we're, in terms of elevation, we are much lower down. And so we think what's happening here is that the hydrothermal fluids have their own path, and they emerge here and form the Banyupayat River. You can also see Marapi volcano up here. It's very high, and so there's a lot of rain that it captures, and some of that rain will also flow down. And this is the lowest part, so we get this flow always in this direction. Okay, so the fluids from the Crater Lake and the Banyupayat River are very extreme. And so they're maybe not the most acidic in the world, but they're very close. So these are warm fluids, about 40 degrees in temperature, extremely acidic. So if you measure the pH, it's about 0, and they're very concentrated. And so we express the concentration of the fluid in a property called TDS, totally dissolved solids. And that is, if you take a kilogram of fluid from the lake and you would evaporate it all, you end up with about 100 grams of solid material. And so this is extreme. This is very, very high. And just to put that in perspective, so this is the pH scale, which goes from 0 to 14. Neutral fluids, such as, for example, what you find in bottled water, are about a pH of 7. And their total dissolved solid load is only between 0.01 and 0.3 grams per kilogram. And compare that to the 100 grams of Kawa Ichian fluid. So this is extremely concentrated. And then if you go down the scale to more and more acidic compositions, orange juice is here at 4, lemon juice has a pH of about 2, the battery acid in your car has a pH of 1, and then this is Ichian waters. So they are even more acidic than the battery acid in the battery of your car. And if we compare it to seawater, we always think of something that is already quite concentrated, but even seawater only has 35 grams per kilogram of solid material, and Ichian waters have 100. So these fluids are really extreme. And that makes them interesting for many things. So if we look at, so let's start looking at the lake here. So if we want to understand the composition of the lake, so we know that this is a very concentrated lake. So how did it get that composition? And so we can think of all the different sources of material that go into the lake. And so one is groundwater that is flowing down from Gunung Merapi, entering the lake. And we can actually see that because we see on the surface that there is a different colored water on that side of the Crater Lake. We have rain, of course, quite a lot of rain into the lake. Then we have these magmatic gases that are coming in. We may also have directly fluid from the hydrothermal system that are getting into the lake. And then if you look at the sides of the crater, they're extremely steep. And so as a result, we get also a lot of rock falls into the lake. And if you spend any amount of time down at the crater, you often hear these rock falls and rock slides that are falling into the lake. Now, when these rocks get into these waters, because they're so acidic, the elements are leached from them. And so this is how we build up that concentration in the water. And then we can also think about how elements would leave the crater lake. So water can obviously leave by evaporation. And if you look at the lake is warm. You see gases actually coming out of the lake and steam rising from the lake. We've talked about the seepage already. So waters are leaking out of the crater lake through the rocks, forming this Banyupait River. And then we have minerals precipitating. And so we see gypsum, for example, but also lots and lots of silica. This is all that white material that you see everywhere around the crater. And if you look at the satellite image of Cave Ichian, you see these white colors everywhere around the crater, but also along the river. Okay, so these are all the potential sources and sinks. So what we did is we studied all of these. We measured their compositions. We tried to determine the fluxes. And so the picture that comes from that is quite an interesting one. So if we look over time, so this is all the data that are available going back almost to when the lake erupted in 1817. We see that the overall concentration of the lake shows a nice gradual increase over time. And the sulfur concentration does the same thing. So that tells us that so the lake was thrown out in 1817, and then we know from reports from about 1820 and 1830 that the lake reappeared very, very quickly. But we see now that the concentration of that early lake was very dilute, and then it concentrated over time. That kind of trend tells us that the hydrothermal system did not contribute fluids directly into the lake, because those would have been very concentrated from the beginning. Instead, we think that the lake is more like a bathtub, or a bucket, if you like. So you have this depression. It filled up with rainwater. Gases were then emitted into that water. And these gases bring with it the acidity. So they make the fluids acidic. And then as rocks fall into that lake, they start to react and release the elements within them. And so that slowly builds up the concentration over time. And then fluids leave by seepage and evaporation. So this is our model now for how the lake operates. And so this is quite important, because that tells us what elements we should monitor if we want to understand changes in volcanic activity. But let's have a look now at this alteration. And so I've mentioned this several times now. So what this is that the fluids from Cave Ichian are extremely aggressive, which means that if you put a rock in these fluids, then that rock gets leached of its elements. It gets changed very rapidly, in fact. And you can see that in the field. So here, for example, we have some lava, and here as well. Here we have a fracture that went through that lava flow, and Ichian fluids passed through. And you can see these layers of altered material. And so here we have the original basaltic andesite. And then progressively, the color of the rock becomes lighter and lighter. And this is because the elements are being leached from it. And what we end up with is this light-colored material. It's almost pure white. And it's almost pure silica. So all the elements that were present in the rock have been leached into the fluid. And if we analyze the compositions of the original material and every layer here, we see that as well. But let me first have a look at some of the, if you look in detail under the microscope, what does it look like? You can see that here for different minerals. So this is the mineral plagioclase. And all these things here are where the fluids are starting to break down the plagioclase. You see the same thing for the pyroxene. Along these fractures here, it's being replaced by silica. And then this is an oxide grain, titanomagnetite. And in this case, the iron is more mobile than the titanium. So you end up with this almost skeleton of titanium, and all the iron has been leached out and is full of holes. Okay, so I said, so let's look at the compositions. So what I'm plotting here in red is the compositions of all the Ichian lavas. So these are the magmatic deposits, unaltered, and this is their compositions for different elements. And they show some variability because of fractionation. And then these are the altered rock compositions. And so this is the trend of progressive alteration. So it started out with this composition, and then as the alteration progressed, you can see here, for example, for aluminium, that the aluminium content goes all the way from here to almost zero. And we normally think of aluminium as being an immobile element, but the Ichian fluids are so acidic and they have so much sulfur that they are able to mobilize aluminium and to really leach it from the rocks. And almost all the elements show the same kind of trend. The only element that really shows a strong enrichment is silicon. And that is because that's residually enriched. So, so this has a very, very strong impact on the composition of the fluids, because all these elements are being added then to the fluid. Now, to understand this better, we decided to do an experiment to basically do the same thing. So we took a little fragment of one of the 1817 deposits. We put it in this test tube with Kawa Ichian Crater Lake water. And then we left it for 42 days at 25 degrees to see what would happen. And so this is similar to what happens in the riverbed and in the lake when rocks fall into the lake and they start to interact with the fluids. And when we then look at the minerals, you can actually see that we see very, very strong alteration and leaching. So this is the plagioclase crystal again. And all this in the middle, you can see that that has been very thoroughly destroyed. And the material that remains is opal, silica, and everything else has been leached and put into the fluid. And we can analyze the fluid and see that as well. And so what this allows us to do is we can now calculate for different types of materials, so scoria, which is very porous, but contains a lot of glass, and then lava flows that are full of minerals, the amount of elements that are added to the river every day. And this is just by this alteration. And so you can see here, for example, for scoria, we get about a kilogram a day of lead that is being leached from the rocks and added to the river. Okay, and so what we can do then is if we know this flux, we can take the composition of the lake water, we know the alteration, and we can plot one against the other. And when you do that, almost all the elements show a beautiful one-to-one correlation. So they are exactly on this line. And that tells us that the elements in the lake are indeed coming from the rocks being leached and then going into the lake water. And we can even calculate how much. So if we take 1 kilogram of lake water now, that contains about 40 grams of andesite. So andesite has been dissolved and put into that. There's a few elements that don't fit that pattern. So these ones here, and that is because they are precipitated from the lake water. So they're at lower concentration than we would expect. Silicon, for example, we know that that precipitates. We see silica lake sediments. Barite is a barium sulfate that is depositing as well. And then we have some elements that are enriched as well. And these ones we think are coming from the volcanic gas. So it's not just rocks going into the lake, but the volcanic gas as well. So they add additional elements. So this is then the how we think that the lake actually works. So it's like a bathtub. So it filled up with rainwater, gases made it acidic, rocks led to all the elements that we find in here. And then we have the fluids are seeping out, forming these springs on the side, as well as the evaporation and so on. And the volcanic gases itself, they're coming from this magmatic vapor. Okay. So let's go now and talk a little bit about what we can say about how things changed over time. And because we now, from the study of the rocks, the study of the gases, the study of the fluids, we have a pretty good understanding of where elements come from in the Ichian system. So what elements come from magma, what elements come from groundwater, what elements come from rocks, and so on. And so that is very useful, because that kind of understanding then allows us to see, okay, if now the composition changes, what is happening to the volcanic system? And for monitoring, that is of course very important, because if you need to understand, okay, what does it mean if the concentration of an element goes up or goes down? What has been changing in the volcanic system? And the problem is that, of course, for the past, we don't have these fluids anymore. And so we cannot look at the composition of the crater lake 50 years ago or 100 years ago, because we simply don't have those fluids anymore. So as a geologist, what we do then is we turn to the rock record, because the rock record is preserved. So that can actually tell us something about these past compositions. And at Ichian, what we focus on is on the mineral gypsum. And the reason for that is that at all these springs that I've shown you, gypsum precipitates. And especially at the upper springs, we get a lot of gypsum precipitating. And you can see that here. So there's a scale bar of about a meter, this huge amount of gypsum precipitating from the fluids. And it has been doing so for a long time. And so gypsum is a calcium sulfate, and it precipitates where these fluids, so they come out from the seepage springs. There's very little gypsum precipitation first, but then as these fluids cool and water evaporates from them, so their concentrations go even higher, we start seeing lots and lots of gypsum precipitating. And we also find it, if you look at the level of the lake, so right at the shore, you see gypsum precipitating, and at different levels on the lake shore. So that tells us that the lake level has been going up and down. And we even found gypsum in phreatic deposits. So we know that gypsum was present, for example, in the 1817 eruption, but also it's much older. Okay, now, when a mineral forms from a fluid, then it kind of captures the composition of that fluid. So if there's equilibrium, then elements will exchange between the mineral and the fluid. And so the composition of that mineral reflects the composition of the fluid. And so we see these gypsum needles here growing out of this Ichian fluid. And so the composition of that gypsum tells us something about the composition of the fluid from which it formed. And this gypsum is very interesting because it shows layers. So here you can see these color variations. Here more clearly, you can see really nice layering in the gypsum when you look at the cross section. And this is similar to tree rings. So we know that this gypsum has been growing for quite a while, and every time it grows, it stores a new composition. So we get a history of how the fluid composition changed through time. And we've been able to determine that the growth rate is about 2 millimeters per year. We also find these stalactites of gypsum. And these stalactites grow faster. They also show very nice growth zoning. And because they grow faster, they then give us even higher time resolution. And so we can look at variations on a smaller time scale, such as seasonal variations. Now, if you want to do something with this, we need to know how old every growth zone is. And so for that, we do dating. And there is no, so one way to date this would, for example, be using carbon-14, which we use for charcoal and plants. We can't do that for gypsum, simply because there isn't any carbon-14. But what we can do is we can use something called lead-210. This is a naturally occurring isotope of lead. It has a half-life of about 23 years. So we can use that to date the gypsum. And for this specific stalactite, that tells us that the core of this gypsum is about 40 years old. So this stalactite can tell us what has happened in fluid compositions over a period of about 40 years. We also took a very large section through the gypsum, and we dated this one. And this actually already gives us information all the way down to about 1920. And so we can date these different growth horizons. So here we're about 1920, 1940, 1960, 1990. And this gypsum was still growing when we sampled this in 2009. So we know that the surface here grew in 2009. And so this provides us with almost 100 years of changes in water composition. And the 1920 is quite interesting as well, because this is the time where we have the earliest photographs of what the system looked like at that time. So here you have your dam, the dam again, and water flowing. And the gypsum plateau would be here. And it appears that this picture shows there was no plateau at this time, which would fit with the time scale that we have here. Although this is something that we would be very interested if people have information on the gypsum and when they first saw it and so on, because well, we're not absolutely sure when it first formed. Okay, so what we do then is we analyze the composition of that gypsum along that whole transect, and we see how it changes for all the different elements. So we look at metals, and we look at how these things changed from here is about 2010 all the way down to 1920. And you can see there's quite a lot of variability in that record, especially in the more recent times. And that variability involves the elements that Kim's research on the gases are telling us something about magmatic degassing. So for example, copper showing this really strong spike here. And we know that copper relates to deep magma degassing. So this sulfide liquid. And then we see other spikes here in antimony and arsenic. We don't really see in the copper signal. That suggests that this is degassing from the shallow dacitic magma. So there are some, so we see different signatures in this record. This is the recent data on the seismicity and rain in the system. And you can see that that only goes back to about 1993. And unfortunately, we have nothing here. So gypsum really is then important because it can extend this record back in time and tell us what's happening. And here, for example, as well. And then what I'm showing in these orange lines, these are reported events of volcanic activity. So here, for example, in the 1950s, there was a phreatic event. And then here in more recent times, we have some events as well. And in some cases, we can actually link these. Here, for example, there seems to be a copper anomaly at the time of one of these events. So we can start recognizing these in the pattern. But this is quite interesting. And because we understand where elements come from in the Ichian system, we can link them to what's happening in the deep system. Now, just to give you a sense of scale, so we see these excursions in copper. Now, we actually also have gypsum from 1817, and its copper over strontium ratio is all the way out here. So even though we see variations in the copper signal, they're nowhere as big as what happened in 1817. So that was a much bigger event than what we have here. Okay. So now I'm going to hand over to Kim again.
Right, thank you. So as Vincent showed, this is now the last part of this presentation. So as Vincent showed that we have quite a good understanding of where all the elements come from, and we can start to use that in order to interpret what might be going on at the volcano. So next slide, please, Vincent. So one thing that would be really interesting to look at is, of course, these gases, because the gases arrive at the surface now, and they can tell us what might be happening in the current day underneath the volcano. As I mentioned before, sampling of the gases at the fumaroles is a challenge. There's a picture over here of what happened to a temperature logger that was stuck into the fumarole. The equipment just doesn't last long enough to get more time series data. So we've been looking for a different way to analyze to monitor the gases and the fluids that are coming out of Ichian, and ideally at one that doesn't require access to the crater, which is not a place you'd want to be should anything start to show signs of activity. Okay, so we've settled on looking at the fluids at the Banyupai River, and they're being sampled all the way at the bridge, so quite far away from the crater itself. The fluids have the advantage that they have direct access. They give us direct access to the hydrothermal system, as Vincent explained. Most of the fluid in that river is, in fact, hydrothermal fluid. And the problem is that these fluids are a combination of different fluids, seepage as well as the hydrothermal, and then all the things that happen, all the alteration that happens along the riverbed, as well as neutral groundwater coming in, precipitation of crystals. The good news is that we've looked at most of these things, so we know what happens, which elements are contributed by alteration. We know what the composition of the lake looks like, and we have an idea, because we sampled the springs, what the hydrothermal fluids looks like as well. So we can start to tease apart these fluids and see whether we can actually see something, some change, and relate that to actual processes when we monitor these fluids over time. So this is a project, next slide please. This is a project that was set up in collaboration with the Ichian Volcano Observatory. And the observatory staff has been taking samples between late 2015 into 2018, every week or every 2 weeks. These samples were analyzed in the field for sulfate and chlorine, and then they were sent to McGill University for trace element analysis. So this period, 2015-2018, includes this gas bursting event that was in the news in March 2018. Next slide, please. So here we have a plot. This was published in 2020. And we see at the bottom, you can see how the precipitation changed over this period of time, as well as the sulfate and chlorine over chlorine ratio that was analyzed in the field. And you can see a couple of different elements, strontium, lead, and how they varied over time. First off, what you note is that there is a seasonality. All the elements, the trace elements, behave very similar. So there appears to be not much happening there. There's just simply dilution with rainwater as it starts to rain. The other thing you should note is that on the left side, I've plotted in the concentration that was obtained from the gypsum. Sorry, can you go back, please? On the left side of the image, you see that blue bar that indicates the composition of the fluids as it's calculated from the gypsum. And what we see here is that the concentration of the fluids that was analyzed over this period, 2015 to 2020, is not different from what has been, but the composition has been over the last 100 years or so. So it's pretty much this period was nothing but business as usual. Nothing strange happened, nothing out of the ordinary. It's all within the what we'd expect for Ichian. Next slide, please. Okay, so then we need to look a little bit deeper, and instead of looking at a single element, we can look at how multiple elements behave together. This gives us a way to see through that seasonal variability. And what we've done is we did something called a principal component analysis, which is essentially recasting the data in terms of processes, the principal components based on the variance of the elements in the data set. And so now we can start to compare our data to the actual processes that we know are happening and which we've all have data on in previous work. So dilution with groundwater, alteration, different types of alteration, seepage from the lake. We can all start to tease that composition of the fluids apart and then plot it along a time series data. And we can start to see that there's different patterns occurring. So we can still see a little bit of seasonality, but there are other underlying patterns. So in 2015, 2016, are pretty much the same thing happened. Nothing much happened, very, very similar compositions. But then in 2017, there's an increase in groundwater flux, which leads to, next slide, please, Vincent, which leads to an excursion early in late 2017 and into 2018, which is something that we didn't see before. So this is mainly made up by copper, but there are other elements associated with it. And so we've seen that copper is something that's coming from the deep system, potentially from the magma. And so this could be related to something happening in the system prior to that gas bursting event. Exactly what was happening is still a bit unclear and requires some further work, but we can actually see a change happening associated with this event. Okay, so this concludes our presentation. Next slide, please, Vincent. We'd like to thank you very much for this invitation. It's a great honor to be able to present this work at this forum. And we hope you've enjoyed it, and that if anything's unclear, please ask us questions. Ichian is a fantastic place. It's beautiful, but it's also very interesting for scientific research. It's a very unique place where we can do lots of interesting things and where we still don't understand a lot of things. So there's still a lot of work that needs to be done here. Next slide, please. None of the work that we presented here today would have been possible without the help of the local population, the support of that population at every visit that we've made over the years, as well as all our international collaboratives and funding agencies as well. Thank you very much.
Okay, thank you, Ms. Kimberlo and Mr. Vincent, for the great explanation. As we know, Ichian is really great place to volcano researcher with the acidic lake and blue flame, of course. And then before the Q&A session, we will go through Firman. Maybe you have some response as the region geologist of Ichian Geopark. Please, Firman.
Okay, thanks, thanks so much, Vincent and Kim, for the talks. Very interesting for us. We hope that your explanation about the geology of Ichian volcanic complex give us a better explanation about the phenomena. Yes, Ichian not only about the crater. Yeah, the explanation from Professor Kimberlo is very nice about the Ichian caldera. That something we don't fully understand how the caldera erupts, where is the products, and what is the mechanism to trigger this big eruption. And the main question is about what will the future? Is that any potential for a caldera forming eruption like the old Ichian caldera? Maybe this is some short question that we can doing together in the future, maybe with you, Vincent and Kim, to do progressive research in our geopark, Ichian geopark. Maybe this is my response. Thanks so much again.
Okay, thank you, Firman. Yes, please, Ms. Kim and Mr. Vincent, maybe you can directly to respond.
Yes, thank you for the question. The caldera forming eruption is something that's really interesting. I haven't been able to look at that much myself. It's quite inaccessible. I mean, the locations that we visited were not great. It is definitely something that needs to be looked into. It's quite an old eruption. It's an older caldera, and really. It is one of the big questions of Ichian, exactly what happened during that eruption. And even how old it is still, there's a very big error bar still on that age. So definitely that is something that needs to be looked into in the future.
Yes, thank you, Ms. Kim. That's the response from Firman question. There is several potential to increase the research potential in around the Ichian volcano. So maybe there is a question from the participant. Please, you can use the raise hand and you can directly ask question to the Miss Kim and Mr. Vincent. Yes, please, for everyone, participants. Or maybe I will read some question from the chat. We have two questions from the chat. The first one from Sahrul. I'm Sahrul, the indigenous people of Ichian Geopark. Can the acidity of Kawah Ijen extremely change from acid to neutral, even that's basic?
Yeah,
Yes, please,
that's a good
Mr.
question. So I can answer that. Right now, it would not be possible to change it very much. And that has to do with the fact that the lake is very, very large. So we have almost 30 million cubic meters of water. So if you want to change the pH of such a huge volume of water, you would need to do something really dramatic because there's so much acidity. And in fact, you cannot make the lake more acidic because it's about as acidic as it possibly can be. So very much more acidic is not possible. But to neutralize it, you would need to put something into the lake that neutralizes the acid. Now, the rocks that are falling into the lake do that in part. So they react with the water, and that reaction neutralizes the waters. But at the same time, we also get volcanic gases coming into the lake. So that offsets the two things. And in fact, we see that it stays roughly the same. So if the input of volcanic gases would stop, and you have enough time, then over time, the acidity of the lake will decrease. It will never become alkaline or basic because then you have to have a different type of volcanism. So in that case, you basically have a lake that is filled with rainwater, and only CO2, for example, would go into the lake, and that can or rocks and things that can change then it into an alkaline lake. But if the lake is thrown out in an eruption, then what we would predict based on the data that we have is that the very first lake that would reform would be mostly rainwater, so that would be closer to a neutral pH. But the lake is so large that you cannot really change the acidity of the lake any other way than just throwing it all out and starting a new lake.
Okay, thank you, Mr. Vincent. The conclusion that that is possible, but it's hard to happen, maybe.
Yes.
Okay. That's all, Shahrul. Hope that can answer your question. And then we move to the next question from the Mr. Andy. Could you please open mic or raise your hand, Mr. Andy?
Okay, thank you very much.
Okay.
Yeah, I have questions. This is very, very interesting, and thank you very much for the lecture. I'm actually, because I'm Indonesian tourist guide, and this is very, very interesting that maybe can do this regularly. Must be very, very good for us. So my question is actually maybe simple, but sometimes this is a lot of question from my tourists. The question is lately when I see the blue flames, and also I went there before, it's like a month ago. So I saw it that the blue flames like more or less and then lower. So some people said from the miners, so they said maybe because there is like a geothermal in Kawah Burung or Crater Burung that also located inside of the caldera. So Dr. Vincent, is there any relation that a blue flame which is now lower and then very little? Some people say because the miner always pour water, this is to kill the blue flame, or because there is also relations caused by the geothermal that was established last year in Kawah Burung. Thank you very much.
Yeah, so this is an interesting question, and so it relates to okay, so what are the links between Kawah Ijen and its activity and different parts of the caldera? And so we know that there are links. So as Kim showed, there is this linear trend through the caldera that links all these small volcanoes that are inside the caldera to Kawah Ijen. And so that would be Kawah Burung, Genteng, Anyar, all these small volcanoes, they're all along this trend. Right now, we don't really understand what this trend is, whether it's a dike or a fracture zone or something. But in principle, that links the volcanoes together. However, so the drilling for geothermal energy in Kawawurung is very unlikely to impact the blue flames. And that has to do with the fact that the blue flames are actually not a natural phenomenon at Kawa Ijen. So to get this, this burning of the sulfur, the temperature of the fumaroles and the gas emissions needs to be higher than about 350 degrees centigrade. And so we've measured the temperature of the gases directly at the top of the fumarole mount, and they are about 300 degrees or so. And so locally, the temperatures are higher. So locally, we've measured temperatures up to 600 degrees. But every time that we measured higher temperatures, it was because the gases were essentially on fire. And so the gases coming out of the fumarole mount are not hot enough to the self-combustion. And so the only way to get the blue flames is then for someone to light the flames. And so someone to actually use a match or something, or a lighter to light the sulfur and make it burn. And so we have reports from the 1990s that basically there were no blue flames. And so it seems that maybe by accident, maybe on purpose, these blue flames were then created when the gases and the sulfur were put on fire. And so what we know is that so when this happens, this process, you burn away the sulfur. So the sulfur miners are not a big fan of this, because this means less sulfur for them to mine. And so there is, so I can see that for the tourists, of course, this is one of the biggest attractions. And so they want the biggest blue flames they can probably see. For the miners, there's probably better not to have too much of the blue flames because they would lose sulfur. So I think that is the bigger reason for changes in the amount of the blue flames that you see. So it is basically what happens to be on fire. It is so the flames will keep going, but over time the flames will go out if nobody continues doing this, simply because the gases are not hot enough. And so because of that, we can also say that it's not linked to what is happening at Kawawurung. This is where geothermal fluids are being extracted so I have some samples from the altered material in Kawawurung. The alteration looks very different from what we observe at Kawa Ijen. The fluids are not as acidic. So we don't really know the pH of these fluids, but they're not very acidic. So even the geothermal system is not linked to the hydrothermal system of Kawa Ijen. These are two separate systems, different fluid sources, different fluid compositions. So I don't think that this is the reason why you see changes in the blue flames. I think this is more to do with how much of the fumarole mount is actually on fire.
Okay, Mr. Randy.
Thank you, Dr. Vincent. Maybe may I have second questions, because this is very interesting now. I'm really interested. So the second question is maybe for me is very important, because I'm a volcanological tour guide specially. So I have questions like integratedly. So the color and then the composition, the mineral, especially I saw like there is like a small fragments, like globules, like globule sulfur, like that. So what caused that globule sulfur, Dr. Vincent? So because sometimes I have question about this when my client, my guest, they are geologists, so they ask me to collect or to get some globule sulfur. So what caused this globule sulfur? Maybe from efflata, from product of eruptions, or from precipitation, or from sediment. So thank you, Dr. Vincent.
So can you repeat what it is exactly that you found?
Globule sulfur is globule.
Oh, globule sulfur.
Yes, globule sulfur. Yes.
Okay, so
which is existing now in Ichian, yeah.
Yes, so we have multiple types of sulfur that are present at Kawa Ichian. And there is, of course, the sulfur that is condensing from the fumarole mound. This is coming from the pipes. First is orange liquid sulfur, and then it crystallizes to these thick layers of yellow sulfur. We see some of these sulfur that flows all the way down to the lake. And then it turns from a yellow color to more of a greenish color. And this is two things. One is it's picking up other elements that change its color, but there's also a phase change, so the crystal changes the sulfur type. And then we have sulfur that is present. So when you actually walk down along the path down to the fumaroles, you pass some layers of sulfur in the walls. And these are old lake sediments. So this is sulfur that's deposited on the bottom of an older lake. And so this is also yellowish to greenish in color. And sometimes you find these little spheres, globules of sulfur in that. And then if you look at the lake itself, you have these globules of sulfur and ribbons and almost ropey sulfur that is on the surface of the lake. And so this is what forms, so we think right now that there is sulfur at the bottom of the lake, and gases, as Kim showed, pass through that. And these gases, so they get a coating of sulfur around the gas bubble, and then they float up to the surface. And so we have these little spheres of sulfur. And we also find ribbons and ropey textures and things like that. We don't fully understand how this forms. Maybe some of the sulfur actually flows all the way into the lake, and maybe there it cools very rapidly and forms this ropey texture. But so these are things that they're related to the fumarole gases coming out, interacting with the lake water, most likely. So Kim, I don't know if you have something to add.
Yeah, thank you very much, Dr. Vincent. Yeah, that's very good for me.
Okay, thank you, Mr. Vincent and Mr. Andy. Such great information that geothermal is not likely unlinked with the blue flames in Ichian because the different resources. Okay, the next one. We have Mr. Tato. Yes, please, Mr. Tato.
Okay, thank you, Bigly. Hi, Miss Kim and Mr. Vincent. Thank you very much. Tonight I joined with your forum to discuss about Ichian creature. Okay, I am Tato Octavianto. I am teacher in junior high school. Actually, I'm not geographical teacher, but I'm social teacher. In my country, in social subject, divided by 4 parts: historical, economic, geology, and sociology by 1 subject. So tonight I am very interested in this forum to discuss about your topic. Okay, Vincent, I know about some mountain character in Caribbean, such as in Montserrat Island. Montserrat is part of the UK overseas territory, right? Have the very unique character, and it is same in Caribbean islands such as Martinique Island, French department territory. It has a Python mountain because this mountain character is maybe the same in Ichian mountain. In Martinique Island, Python mountain become in one a good energy to geothermal energy. And I want to know you explain tonight to explain about the character of the Ichian mountain and mountain in Caribbean. Maybe you have the resources to explain to me about mountain character in Caribbean and in Java Island.
Okay, I'm going to pass this question on to Kim, because she has actually worked on Montserrat. So we can explain you exactly the similarities and differences.
Okay, I was just if I understand the question correctly. So you're interested to know what the difference or similarity is between volcanoes in the Caribbean, like Montserrat, and
yes, because I read the some literature from internet. In Martinique Island is part of the French overseas territory. The mountain become the good energy for the geothermal, such as in in Ichian Catcher in Wakahurung become the good energy for geothermal. And I want to know the character of the mountain in Caribbean and in Java Island.
Okay, that's a difficult question. There are probably many differences between the Caribbean and Ichian. One thing that comes to mind is in the Caribbean, we have these small islands. So essentially all the islands are one or maybe two volcanoes. On Java, not so much Eastern Java, but definitely Western Java, there is a bit of continental crust that contributes to that the magma has to go through before it erupts on the surface. So the crust is thicker. Even in Eastern Java, it's thicker than it is in the Caribbean. And that influences the volcanism as well. So what we typically see is that in places where the crust is thicker, we see that the magma spends a longer time traversing that crust, so going through it. And in that time, it can crystallize further, it can differentiate. So what erupts on the surface tends to be more felsic magmas. But that comes with a lot of caveats. There's a lot of, it's not as black and white as I'm painting it right now, but that would be one big difference. So the other thing that comes to mind is in the Caribbean, because they're smaller islands, you have the sea all around it. Whereas in Java, it's bigger. And you'd have more, the fluids are not just seawater. There's a lot more other types of fluids, rainwater, that comes into that too. I'm hoping I'm not making a very good, I'm hoping I make sense here. So there are differences between the volcanoes. Both of them are subduction zone volcanoes, but one would be more toward the continental arc, so a thicker crust than the Caribbean, where you're definitely talking about a oceanic crust on top and an oceanic crust going down. So that would be the main difference, I think.
Yes. Yeah, thank you, Miss Kim and Mr. Vincent. So as a teacher, I need more explanation. I don't know why the Dutch imperialism, looking some new land, have the good land. For example, in ABC Island, Aruba, Curaçao, Bonaire, and in Caribbean, such as Saba Island, so Saint Eustatius, you have the very unique character. So in Indonesia, in East Indies, Netherlands, find the very beautiful land. It's called Indonesia, and they find the good character the same in Caribbean, mountainous such as Ichian, and have the sugarcane land and a farming land and the character of tropical country. So as a teacher, I need more resources or explanation about why this character the same between Caribbean and in Indonesia.
Yes, I don't think I quite understand the question. Saba, which is part of is a Caribbean island, and it's essentially it's sort of the tip of a volcano. It's just a tip. It's very, very steep. There is not much farming happening there at all. Indonesia is also volcanic in origin. Java, the area around Ichian, is very fertile. You can grow lots of nice crops there. Fantastic coffee, of course. So it's very different. I mean, yeah, it's much bigger as well. I don't know what the exact question is. Maybe Vincent has a better idea what.
Well, so if you're wondering why the Dutch went specifically to these areas, I think that was mainly economic reasons. So it is not that they went for specific volcanic settings. I think by the time that people went there, their understanding of volcanoes was very, very limited. And so it is maybe more coincidence that the ABC Islands are volcanoes as well than anything else. So I think these were mainly economic reasons. Yeah, so I don't know if you've ever been to the Netherlands, but we have almost no rocks. So as a geologist, there is very little to do in the Netherlands. And so I know that many Dutch geologists would definitely go to Indonesia, and they would go to the Caribbean to study the rocks there. But yeah, the reasons were economic, I think.
Okay. Thank you, Mr. Vincent and Miss Kim. Thank you very much. Kembali ke Mas Vicky.
Okay, thank you, Mr. Tato, for the great question. So the conclusion is every single area who contain the mound is exactly different because we have the own character of the area. Okay, the next question I will read from the chat. From Miss Tantri. Could you please open mic or something, Miss Tantri, or maybe just from chat? Okay, maybe I will read from the chat. From Miss Tantri Raras, from the Ichian Geopark Management too. There is there in 1870 eruption of Kawah Ijen produced pyroclastic flow, because in 1814 early people that inhabit in Ijen caldera create a singa-ulong dance. It's contain local diversity maybe. Lion with white for all over its body. That is this related with pyroclastic flow phenomena? It's possible, or maybe just that.
Yeah, so this is extremely interesting for us as well, because this is the kind of information that can really help us understand what happened in the past. Because there is very little documentation about Ichian until about 1900. So before that, it's very hard to know what happened to Kawah Ijen. And so this kind of thing, and this kind of local song or records and things are extremely interesting because they must relate to something that happened. And as researchers, we can try to find out what this relates to. And so we know that 1817 eruption was a very big event, and it really impacted many people. It did not produce a pyroclastic flow, but it did produce lahar flows. And these lahar flows went to three directions. So they went to the north, and they went all the way to the Asam Bagus plain, and they probably flowed into the ocean as well. Another one went to the east, and a final one went down and flowed past Lichin and then all the way to Banyuwangi. And so these were not pyroclastic flows, but these were lahar flows that contained a lot of altered material, because the lake was there, the rocks were very altered, and then they take on this very light colored, maybe white to light yellow color. And so we know there are some descriptions from people in Banyuwangi in 1817, and they described this white mud that smells of sulfur that is coming down the rivers, and it is flowing over the farmlands, and it flows all the way into the city. And yes, this could be indeed how the local people have managed to turn this into a song and describe in this flow of essentially a mud flow or lahar of altered material coming down the volcano. And if there is any information in this song about what that looked like or how people dealt with it, I would be extremely interesting to know about this, because it could help us understand where this flow went and how it affected people, and also how long it lasted, because this is something we, for example, do not know.
Okay, thank you, Mr. Vincent. Actually, yes, of course, because we had very less documentation about the linking between the eruption and the culture that form in the society. But there is quite interesting to do some research for that. Okay, the next question we has Shahrul again. It is possible that biota can live in Ichian acidic crater because the crater is, hyper acidic. Yes, please.
Yeah, that's a good question. And people have looked at this in the past. So what they did is they took water samples from the crater lake, and they analyzed the DNA in the water samples. And they were specifically looking for bacteria that can withstand the very acidic conditions. And it is my understanding that in the crater lake itself, they found no organisms that are living in the water. And not so much the acidity that is the problem, but it's the fluorine content. And so the fluorine content is quite high. It's about 1,500 milligrams per kilogram. And fluorine is very toxic to organisms because it binds very strongly with calcium, and you need calcium for your cell mechanisms to work. And so then the calcium is no longer available and it doesn't work. But what they then found is that if you go to the springs of the Banyupait River, you do find organisms living there. And these are called acidophiles. So these are organisms that can actually withstand these extremely acidic conditions and can survive. And so if you go where the road crosses the Banyupait River, when you come from Paltuding and you drive to Sempel, if you look at the rocks that are lying in the river and you turn those over, then they're covered with green material at the bottom. And these are organisms. So once the pH rises a little bit and it goes to about a value of 0.5, and the fluids are more dilute, so the fluorine content has decreased to maybe 500 or so, it seems that organisms can live there. But in the lake itself, the only DNA that they found was material that fell into the lake. And but it doesn't seem that there are any organisms living in the lake water.
Okay, of course, it's very hard the organism to live in that lake. Okay, the next one from Mr. Slamet. Could you please open mic, Mr. Slamet? Okay, maybe I will read from the comment. I'm Slamet. Why the color of Ichian crater lake often changing? Sometimes green, but another time is a little bit almost white. Yes, please.
Yes, this is something that we have observed as well. And I think it has to do with how the lake is being mixed. So we know, for example, that after heavy rains, the top layer of the lake becomes quite dilute. So the interesting thing is that normally when we think about mixing water together, then we think that it mixes completely. But the crater lake fluids are so concentrated, they're so dense, and they actually are quite viscous as well, that it's like mixing oil and water. It doesn't mix, but one floats on top of the other. And so we see that with rain. The rainwater forms a dilute layer on top of the very acidic waters of the Ichian lake. And then, but over time, they start to mix. And this is in part because the gases that are passing through are stirring the lake. And so what you sometimes get is that you have this layer on top that is more dark blue and it doesn't have this greenish blue color that is normal. So that is where we get this dilution of rainwater or sometimes even groundwater that changes the color. And then what happens is that once in a while we get that the gases coming into the lake are more vigorous. And so you get these burps of big gas slugs that are passing through the lake. And they're stirring up sediment that is at the bottom of the lake. And this sediment is mainly silica. So these really strongly altered rocks leave a mud that is almost pure white silica. And when that gets stirred up, that changes the color of the lake from this greenish yellow color to white. And so these changes we've seen, and they're related to changing in how the lake is stirred by different things. And then the final thing that happens is, so sometimes we see that the temperature of the lake rises very rapidly, and then we see a lot of evaporation. And then you can actually get gypsum crusts forming on top of the lake. And I believe this happened last in 2014. No, sorry, that's not true. Possibly later, 2016 or so, when a crust of gypsum formed on top of the lake, and then it becomes very white in color as well, so grayish white. So those are the reasons that we see in the color changes. And the final thing is what Kim showed in her presentation. We get sulfur floating on the lake as well, which gives this yellow color. So sometimes that is very concentrated, and sometimes the wind pushes all of that to the sides and you don't see that. So those would be the main reasons why we get color variations.
Okay, thank you, Mr. Vincent. Maybe there is the last question from me. This is related to several issue in Ichian Geopark. You know, like we have the outstanding geology such as acidic lake and blue flames and so on. But I need confirmation from you both, Mr. Vincent and Miss Kim. What do you think about the Ichian acidic lake is the most acidic lake in the world? Maybe you can.
It's not the most acidic. So there is a lake in Costa Rica called Santa Ana that is more acidic.
Okay.
Ichian is the biggest acidic crater lake in the world.
Okay.
And so it is by far the biggest. So it's maybe in terms of its pH, not the lowest you can possibly get. And so Poas volcano also has an extremely acidic crater lake, but it is much, much bigger than Poas, and it's much, much bigger than Santa Ana. So it's not the most acidic, but it's the biggest acidic lake.
Okay. So the bigger acidic crater lake in the world. That's right. Okay. The next one is how about the blue flames? Sometimes the local people say that the blue fire or blue flame, there is two in the world. The first one in our region in Ichian, and then the second one in Iceland. But probably we never find the proof from the blue flame from Iceland. Maybe you can give any response to educate the local people about the blue flames, or maybe there is another blue flame in the world except in Ichian or something, maybe.
Yeah, so I think I should pass this on to Kim because she's done a lot of work in Iceland.
I've never
Yes,
actually
please,
heard. I've never actually heard of the blue flame in Iceland. As Vincent explained, it's probably not a natural thing. So maybe somebody just lit the sulfur there as well. And if that happens there and it can happen at Ichian, then it can happen at other places as well. So it doesn't have to be a unique phenomenon. So you could light sulfur elsewhere and you get blue flames. Is that correct, Vincent?
Yeah, I think that's true. So I know that there is apparently another place that has these blue flames, but really what is happening is that you have superheated gases that emit light when they cool down. And it is mainly sulfur that is emitting that light and making the blue color. And sulfur is emitted by many volcanoes. And there are other volcanoes that are at the temperature range where you could get spontaneous combustion. If we think, for example, at Gunung Merapi near Jogja, there the temperature of the fumaroles are high enough that you could get this as spontaneous combustion. But at the same time, when it's very hot, you don't have a lot of native sulfur around because it's too hot. So I think at Ichian, we have this combination of lots and lots and lots of sulfur, because if you look, the fumarole mount is completely covered by yellow sulfur everywhere. So that is because the temperatures are relatively low. And then if you have so much sulfur and it is on fire, you get a very intense blue light. Now, if you go to other places that are higher temperature, because of the high temperature, you don't have as much sulfur. So even though it could combust by itself, there simply isn't enough sulfur around to give an intense blue color. So I believe the only other place maybe in the Afar region. I think I read somewhere that you have some blue flames there. Yeah, I agree with Kim. I would be surprised to see it in Iceland.
Okay, thank you. Maybe this information can the fundamental argument to inform the truth about the blue flames, because this issue spread so large. So every people who visit Ijen always say blue flame. There is two blue flame in the world, in Iceland and Ijen, but the proof is there is no proof in Iceland. So maybe this your opinion will be great things for us in here to educate the local people about that. Okay, maybe just that all the question, because the time is running out. Maybe before we close this session, we have I will present some video about the diversity of Ijen Geopark.
People have eyes, but most of them are not really have. Only he open theirs, everything will be different. Saying good night and good day for tomorrow. After and after. Then what? They fly away with the crowd. Wind and rolling wave gathered into one. want to meet the reef that though the solid rocks, they're important. And the grain of sand that make these all complete. Sure me, they all are breathing. And that is life. What should I deny? And what about me as a human being? Time after time, nature always has its dignity. Dynamic, powerful, yet delicate. It collides, then forms into countless repetition. I realize the process does exist. Between awake and asleep, from one secret to another, and also hope along the journey. This is what nature shows me. A gift. Where lesson, beauty, and future belong to.
Okay, there is some video from us, and maybe this is the last session. I hope you can give closing remarks or conclusion from the discussion from Mr. Vincent and Miss Kim. Yes, please. Still mute. Okay.
So would you like us to do so, or you ask someone else?
Okay. I hope you can give some closing remarks.
Sure. Sorry. Yeah. So for sure. So we want to thank you for giving us this opportunity to present the research that we've conducted at Ichian. I think Kim said so. We're very grateful for all the help that we've had in the past, without whom we would not have been able to reach this this kind of understanding of the system. And we also ask that if well, you are very much involved in the Ichian Geopark. You know the area much better than we do. So if at any point you have some information on the geology, or you have some information on the behavior of the system, to please let us know. So this is the kind of information that is very difficult for us to get, and it is important because we can only go once in a while, and we would love to be able there to go more often, but it's simply not possible. And so if the local people also collect information on the volcano, that is extremely interesting for us to improve our understanding. And so let me just say that that Cava Ichian and the Ichian caldera are incredibly interesting from a scientific viewpoint. They're also beautiful and fascinating. It's a fascinating area to visit. I think we will try to continue doing research there to better understand the system. From a scientific viewpoint, but also to help the CVJHM and the Ichian Observatory monitor the volcano and make sure that if the system changes, that we'll be able to warn people early enough to avoid any big impact on the local population. So thank you very much again for giving us this opportunity. Yeah, we would definitely love to visit Ichian in the future again and continue our studies. Thank you.
Yes, we're waiting for you're coming here. Miss Kim, maybe you have some.
Yes, I echo Vincent's comments. This kind of research is a collaboration between people who directly impacted by this volcano, who live with it every day, and the people who are far away can only really visit every once in a while. And if we do, it'll be very short. Those are the constraints that we have to live with. So any information that you have about the volcano, in a way, you are all the experts about this volcano, and we're just looking from afar, and we need your help, essentially. And so we've been very grateful that we've received so much help already from everyone in Indonesia. And we'd like to thank you for the opportunity to present this, what we have discovered, to all of you. So thank you very much for this opportunity. It's been great. Thank you.
Thank you. It's been a pleasure for us to have you both tonight. This is really great explanation and really great information that can be collect to this next session. We hope really we can collaborate in the future. You as researcher, we as the local people, that we need your information about the volcano or something like that. And the last one, maybe there is the closing remark from Abdillah as the management of Ichian Geopark. Please.
Okay, thank you. Quickly, thanks for the interesting talk this day, Prof. Kim and Dr. Vincent. It gives us a better understanding about the Kava Ichian phenomena. Great speaker, great explanation, very clear and very complete. I hope this forum is useful for all of us, can add knowledge and apply it in daily life. I hope this forum will not be the last, but we can continue in collaboration and other collaboration. Ichian Geopark is very open to collaborate with all researchers in the world so that we can continuously understand the phenomena that exist in Ichian. Maybe in the future, there will be many things that can be done between the Ichian Geopark and McGill University, board research, education, and disaster mitigation maybe. I really look forward to this happening in the future. Thank you. Terima kasih.
Okay, thank you, Abdillah, for the closing remark. Maybe I have some conclusion from this session, but I would like to tell with Indonesian. That's okay to our friend. Oke, terima kasih teman-teman telah mengikuti forum kita pada malam hari ini. Prof. Kim dan Dr. Vincent sangat-sangat mengapresiasi keseluruhan kegiatan ini dan berharap adanya kolaborasi dari mereka sebagai peneliti dan kita sebagai local people yang bergerak yang bergerak di sini, baik itu ada guide, ada guru, ada local people yang memang berdampingan langsung dengan Gunung Ijen itu sendiri, karena memang gunung itu bukan untuk ditakuti ya, gunung itu ada sebelum kita semua dan kita harus beradaptasi dengan gunung-gunung tersebut. Mereka beraktivitas menunjukkan bahwa mereka masih aktif dan bumi kita terus bergerak. Nah, makanya kita sebagai manusia, sebagai makhluk yang sempurna, yang paling muda, harus juga menghormati mereka dan beradaptasi sebisa mungkin dengan fenomena yang ada. Yang pasti dari kegiatan diskusi tadi bahwa saya bisa menyimpulkan beberapa pertanyaan bahwa hubungan geothermal dan juga blue fire itu sebenarnya berbeda. Jadi tidak ada hubungannya dengan adanya eksplorasi geothermal sebagai energi terbarukan di kawah burung dengan berkurangnya volume dari blue fire itu tidak ada karena sistemnya berbeda. Mungkin ada beberapa faktor yang memang itu harus diteliti secara mendetail untuk sistem di solvataranya. Nah, seperti itu nanti mungkin bisa dikolaborasikan secara lebih lanjut. Dan kemudian beliau juga mengatakan bahwa Kawah Ijen memiliki kawah gunung api terasam terbesar di dunia, dan juga mereka confirm bahwa blue fire itu bisa hanya satu-satunya yang ada di Ijen. Mungkin lebih tepatnya adalah satu-satunya blue fire yang berada di kawah gunung aktif. Nah, mungkin seperti itu ya teman-teman, bahwa mungkin kita bisa memperbarui knowledge kita dari edukasi-edukasi seperti ini yang tadinya kita mungkin berstatement bahwa blue fire itu ada 2 di Ijen dan juga di Iceland. Mereka konfirmasi bahwa wah, mereka malah belum tahu kalau ada di Iceland, padahal mereka cukup lama, terutama Prof. Kim yang sudah beberapa tahun meneliti di Iceland. Sangat-sangat kaget jikalau di Iceland itu malah ada blue fire. Nah, makanya salah satu blue fire terbaik yang pernah mereka jumpai itu ya ada di Ijen. Nah, makanya mungkin bisa dikatakan bahwa Ijen ini merupakan satu-satunya blue fire yang berada di kawah gunung aktif ya. Teman-teman mungkin nanti bisa diedukasi, disampaikan ke teman-teman lainnya bahwa blue fire, satu-satunya blue fire yang berada di kawah gunung api aktif itu ada di Ijen satu-satunya. Ya mungkin seperti itu. Terima kasih teman-teman. Semoga diskusi-diskusi ini tetap bisa berlanjut. Terima kasih sudah mengikutinya pada malam hari ini. Oke, thank you Prof. Kim and Dr. Vincent. Such a great experience for us. Hopefully we can meet and we can have another session with another topic maybe, but with this good communication and discussion. Maybe if there is a mistake from us, I'm really sorry, and really thank you for you both to spare your time to discussion in this session. Okay, I will close this session. Thank you, Mr. Kim. Thank you, Ms. Kim and Mr. Vincent, and all the participants. The last one will take a photo. Is that okay? Okay, maybe all the participants can open your camera so we can take a photo together. Okay, maybe I will take the photo. 1, 2, 3. Maybe you can give this. This is the icon of the geopark. Mr. Kim and Miss Kim and Mr. Vincent. Okay. 1, 2, 3. Okay, thank you very much. I will end this meeting. So thank you. Bye-bye.